In this next unit, we are going to talk about how to take samples, make surveys, and correct ways to ask questions. And with this will come a lot of fun stories about stuff done incorrectly. So there are two major categories of statistical techniques that can be applied to data. The first is called descriptive statistics. And in this, you use numerical and graphical summaries to just describe your data. And some examples of descriptive statistics could be things like box plots. We made some of those. 5 number summaries. Things like the mean, the standard deviation, regression lines. All of these things use either numerical or graphical things to characterize the data set that you described. Now, inferential statistics uses sample data to make conclusions about a broader range of individuals than just those who were observed. So some examples that you've seen include this chi-squared test, which is a subset of something called hypothesis testing. And we're going to talk about when it's okay to use inferential statistics to generalize to a broader range of individuals. The fundamental rule for using data for inference. So this says that the available data set that you have can be used to make inferences about a much larger group only if the data can be considered to be a representative with regard to the question of interest. So the kicker is you have to have a representative sample. So, for example, your sample shouldn't be all women or all men, unless you want to generalize to all women or all men. And it should include people of lots of different ages if you want to generalize to lots of different ages. So you have to think about, is your sample a sort of smaller picture of what the whole population you want to look at is? So is the sample a small, we'll say, snapshot of what the larger population is? And actually a really good example of that right now is the state of Ohio. So apparently Ohio as a state has predicted the results of the election for many, many, many years. And that was because Ohio was a representative sample of about what you would see across the country. But that's changing, and so it might be the case that Ohio may not be able to continue to be a predictor of, say, a presidential election because it no longer represents the demographics of the U.S. as a whole. So in each case, briefly discuss whether you think the available sample data can be used to make an inference about a larger population. So the heights of women in a psychology class will be used to estimate the average height of all women at a particular college. So the question you have to ask yourself is, do you think that the women in this psychology class more or less cover a wide swath of women at the college? And the answer probably is yes. There's nothing that says women that are taller or shorter take psychology. So women in a psychology class probably have heights similar to those at the college as a whole. So if you can see no obvious reason that makes this sample different from the larger population, I think it's pretty safe to say that, sure, that's not a problem. Now, what if parents of children attending a daycare facility are surveyed about whether the state government should increase funding to daycare providers to provide lower rates for low-income families? The data are then used to estimate statewide support for increased state funding. So do we think that parents are going to predict statewide support? And the answer is probably no. Parents may have different opinions about daycare than non-parents. And also, only parents who use daycare are actually asked. And their opinions might differ from parents who are able to have their kids at home, for example. So the kicker is that parents of children attending daycare facilities are not a representative sample of sort of statewide opinion. Now recall that the larger group of units about which inferences are to be made, this is the population. A smaller group of units that's actually measured is called the sample. And measurements taken on the whole group of interest, this is a census. When you ask everybody, that's called a census. So a political scientist surveys 400 voters selected randomly from the list of all registered voters in a community. The purpose is to estimate the proportion of registered voters who will vote in an upcoming election. So what is the population of interest? So the population of interest is all registered voters in this area. And the sample is the 400 voters selected. And because we only care about registered voters, this sample is representative. Notice that it would be not representative if we were looking at all eligible voters. If we were looking at all eligible voters. So, for example, people who had never voted before, which could be because they're young or just could be because they never have wanted to. That would be not representative of eligible voters, but is representative of registered voters. So the population you're looking at determines whether or not the sample is representative. Now, in a simple random sample, every conceivable group of units of the required size from the population has the same chance to be in the selected sample. So this just means that if your population is half women, half men, women and men each have a 50% chance of getting into the sample. That's the basic idea. So some advantages of a sample survey over a census. For one, a census might not be possible because it's too expensive or it's too complicated. If you're testing the efficacy of some drug, you cannot possibly give that drug to every single patient that, exists, say, across the country or around the world. You pick a small sample. And the other thing is that it takes many years to plan a census, and much less time is needed to plan a survey. So a survey also might be more accurate, as it's easier to train a small group of workers for a survey than the large group of workers needed for a census. Now, surveys are prone to lots of errors, and some of them are sort of so common that they have names. So the first one is called selection bias. And this is when there's a problem in how you pick your people. So selection bias occurs when the method for selecting the participants produces a sample that does not represent the population of interest. For example, if we looked at a basketball team, to estimate heights of women at a college. The way that you selected women there is such that you only selected tall people, because people who are on basketball teams are going to probably be tall. So non-participation bias occurs when a representative sample is chosen, but some of the selected individuals do not participate. Non-participation bias. This is a problem with mail-in surveys and also, like, say, telephone surveys. And response bias occurs when participants provide incorrect information. This can happen because of how questions are worded and or the way the interviewer behaves. It also could be unintentional. If you're asked to report the things you've eaten for the last 10 years, you probably will predict that you've eaten healthier than you actually have. So just for whatever reason, you don't respond accurately. So refer to the 3 types of bias given above. Which type of bias do you think would be introduced into each of the following situations? Explain. So a list of automobile owners is used to select a random sample for a survey about whether people think homeowners should pay a surtax to support public parks. So will this be selection bias, non-participation bias, or response bias? So I think that a good candidate here would be selection bias. And that's because not everyone will own an automobile. Will own a car. And this would be a really big problem if you were looking at a big city. If we were considering a survey is mailed to a random sample of residents in a city, asking whether or not they think the current mayor is doing an acceptable job. Well, if I get a survey in the mail, it's pretty likely that I'm not going to fill it out, so this probably suffers from non-participation bias. And the explanation being there that many people will either forget or just not do the survey. And so people who design and conduct surveys do tons of stuff to try to make sure that people actually participate. The university has decided to go to an online system of teaching evaluations compared to in-class evaluations. What type of bias might be present in this methodology? So let's just explain that when in-class evaluations happen, the teacher isn't present in the room, it's just the students. So the question is that if you are in a class and somebody hands you a survey versus if you're asked to go on your own time and go fill it out, what do you think is going to be the bias introduced? And it definitely has been my observation that there's been a whole lot of non-participation bias. Non-participation. I mean, goodness, myself, I was in a couple courses and I didn't do the evaluations. Shame on me. So, same thing. Many people forget or decide not to respond. Now, something you see a lot of in media are margin of errors and these things called confidence intervals. So this little formula that we're going to use tells us the accuracy of a sample survey. So this is called the conservative margin of error for a sample proportion, is calculated by using the formula 1 divided by square root n, where square root n represents the sample size or the number of people in your sample. So the amount by which the sample proportion differs from the true population is less than this quantity in at least 95% of all random samples. So if you were to do lots and lots and lots of random samples, the actual quantity is within your sample proportion plus or minus this number most of the time. So when you have survey results in the media, like presidential polls and things like that, you are usually given a number that says this person has a probability of winning that is this, and this is the margin of error. And the way that they probably found that margin of error was did 1 divided by their sample size times 100%. And this estimation is independent of population size, which means that it doesn't matter if population is 1,000 or 1,000,000 people, which is a little bit weird. So there is a formula that depends on the actual population, but it's always going to give an answer smaller than the one given by this formula. So basically, this one is overkill and generalizes more. And what we're going to do with this margin of error is find a thing called a confidence interval. So we have this thing called a 95% confidence interval for population proportion. And for about 95% of properly conducted sample surveys, the interval found by taking your sample proportion minus 1 over that root n to your sample proportion plus 1 over root n will contain the actual proportion in 95% of the samples. That's called a 95% confidence interval for the population proportion. So what this is saying is that if you do many samples, 95% of them are going to contain the actual value of that proportion when you do lots of them. So, for example, a television rating agency produces the ratings of TV shows by asking a random sample of 5,000 households with TV sets what shows they watch. Calculate a conservative margin of error for this survey as a proportion and a percentage. So we use that 1 over root n formula, or 1 over root 5,000. This comes out to 0.0141. That's the proportion. As a percent, that's 1.41%. So the margin of error for finding proportions in that survey is just 1.41%. In a random sample of 90 students at a university, 72 students say that they use a laptop computer. So calculate the conservative margin of error for this survey. So your sample size was n equals 90. So your margin of error is 1 over root 90, which is equal to 0.105 or 10.5%. And that one didn't specify how to give your answer, so either one's okay. Now find an approximate 95% confidence interval for the population proportion that uses a laptop computer. So first you have to find the sample proportion. Just to give it a name, I'm going to call it P. So how many people use laptop computers out of the sample? Well, that's 72 out of 90, which is actually exactly 80%. And the 95% confidence interval, this is found by taking that 0.8 or 80%, and on the low end, taking away a margin of error, so 10.5%, and the high end adding a margin of error. So your 95% confidence interval is 69.5 and 90.5%. And if you wanted to get a smaller interval, you would have to take a larger sample. And it's pretty obvious that when the sample size increases, this margin of error is going to decrease. And when a sample size is made even larger, the improvement of accuracy is relatively small. And because of the whole square root in the denominator of that expression, cutting the margin of error in half requires a 4-fold increase in sample size. So in general, there might actually be a place that is sort of good enough, and increasing your sample by 4 to half the margin of error might not be worth it to you. And let's illustrate that whole 4-fold increase looking at these specific samples. So, and their margin of errors, that is. So if n is equal to 500, 1 over root 500 produces a margin of error of about 0.045 or 4.5%. Notice that sample B, if you have 2,000 people, that's 4 times as many as sample A. And having a sample 4 times bigger is going to make your margin of error half of what it was. So here we have 1 over root 2,000 is equal to about 0.0224 or 2.24%. And that 4-fold thing was definitely an estimate, but notice that what happened is I had to increase my sample size by 4 to, as in 4 times as much, to half the margin of error. And this one, part C, is actually 5 times bigger than part B, so we should see a margin of error that's a little bit less than half of B's. 1 over root 10,000 actually comes out to 0.01 or 1% exactly. So the point is you must do a large increase to your sample size to decrease your margin of error. Now suppose you know that you want the margin of error to be 3%. What should your sample size be? So instead of plugging in an n, you now plug in that proportion. So we're solving the equation 1 over root n equals 3%, which is 0.03. And this is the one of the few places in here you actually need to use algebra. So how to get that root n out of the denominator? Well, start by multiplying both sides by root n. So on the left side, that gives us 1. On the right side, we have 0.03, excusez-moi, times root n. Okay, next, to get the root n even more alone, you have to divide by 0.03. Okay, and that gives us 33 and lots of 3s, 33.3 repeating equals root n. And then you have to ask yourself, how do you undo a square root? What is the opposite of square rooting? The answer is square raised to the power of 2. So take this to the power of 2, this to the power of 2, and probably best to just use your calculator sort of like answer function to use the answer that you had that has all the repeating decimals so you don't get any rounding error. So we end up with 1111.111 repeating is equal to n. Now the only tricky thing is that n is a sample size, so n must be a whole number. And using just a 1111 is going to produce a margin of error just a teensy bit more than 3%. So you have to err on the side of caution. and you must always round up. So n should be equal to 1,112 people. Okay, one more. A college dean plans a student survey to estimate the percentage of currently enrolled students who plan to take classes during the next summer session. In times of budget crisis, they might decide that there won't be another summer session. So the desired margin of error for a 95% confidence interval is to be at most 5%. What is the sample size? So same idea. Set 1 over root n equal to 0.05. So first step, multiply by root n on both sides. That gives you 1 equals 0.05 root n. The next, divide both sides by 0.05. We have then 20 equals root n. And then to undo the square root, you have to square. And this time, no rounding necessary. We see that n equal to 400 is going to be good enough. So we'll learn some more cautionary examples and ways of taking surveys in the next lesson.